Probably an easy one, but I just can't figure it out.
Okay, so in 2.2 he's asking about number 5. Let's see what that looks like here. Again, I wonder if your number 5 is the same as mine.
I can read you the problem.
Yeah, well, here, I'll just look it up here. What is it?
It's x times dy over dx equals 4y.
Yeah, that's what I got. Okay, x times dy over dx equals 4y. Okay, so this looks kind of nice. I think it looks like a nice separable DE, although maybe I got other options too. I mean, I actually only have 2 options in this chapter. It's either separable or the integrating factor method. But separable is nice and easy if you want to go for that. So let me think here. You want to multiply the dx over there. Sometimes I do all this in one big step, but let me just do it a little slower here. I move the dx over there, and then if I want the y's, I think I'll divide by a y, and also divide by an x. Do you guys agree with that?
Yes.
I guess I'll just let the 4 sit where the 4 is. You can do whatever you want with the 4 maybe, but I'll leave it there. So I'll have dy over y equals a 4 dx over x. So that's cool. I got it separated. And now I'll integrate both sides. And when I integrate this side, it's the natural log of y. When I integrate the other side, it's the natural log of x. 4 times the natural log of x plus c. Technically, when you integrate these things, you should have this absolute value, although in this very next step, I tend to lose the absolute value because I think now I want to solve for y, so I want to e both sides. So I'll e this side, and I'll e this side.
Because e to the anything is positive.
And so e to the anything is positive, so if I just write down y, I don't need the absolute value to guarantee it's positive. I think because it's e to this, the next step guarantees y to be positive. That's my explanation. And I'm glad you agree with it. Okay, so now I've got e to the 4 log x plus c. We play this game where we maybe call this e to the 4 log x times e to the c. And actually, I take this 4 and move it up here. So I'm moving over here. It's actually e to the log x over 4th times this e to the c. So a couple little moves there that are interesting.
Really?
So
that was my issue at the end.
Right at the end,
I forgot to move the 4
up.
The logarithmic
Yeah.
property.
Yeah, it was just because I had the different answers in the back of the book.
Yeah,
and
right. So it wasn't a difficult problem.
Yeah, I just
but
wanted
then
to
at
know
the
what I was
end, you
doing
got
wrong.
these are slick little moves, right? I mean, they're not that slick, but they're right. Logarithm using log properties, you can, and e's and logs and log properties, you can really change the look of this. And what is it going to be? It's going to be a multiplied c. We're just going to call that c. And then this e and log cancel. And so this turns into there is no e's or logs in the final answer. It's, yeah. So that's cool. Yeah, that's my final explicit general solution. Right. Multiplied c. Good. Any other good requests anywhere? 2.2, 2.3, 2.5.
I got 1 and 2, 3 if you want to do it.
Sure.
Yes.
If you think you need help with it, yeah.
Yeah, because the answer I got was different from what was in the book. So that means it was wrong. I want to say it was it's 8. Number 8 in the book.
Huh. Okay. And what is your number 8?
My number 8 is x dy dx plus 2y equals 3.
Okay. From 2.3? Oh, x dy dx plus 2y equals 3.
It's our 10.
Okay, I see that. It's my number 10. Okay. So that's okay. In 2.3, my number 10 or your number 8 is x dy dx plus 2y, I think you said, equals 3. Yeah. Yeah, this is a good problem. This is a good problem.
Oh, actually, I'm sorry, it was 9. Now I'm looking at the work.
Okay. And what's your number 9?
It is, it's x dy dx minus y equals x squared sine x.
Yeah, that's my number 9. Okay. So that's the one you prefer.
Yeah, I'm sorry.
Okay, that's okay. So in 2-3 now he's saying number 9, which is x dy dx minus y equals x squared sine x.
Yep.
I think that's what we said. Okay.
You know, I'm looking at the problem, I already see what I did wrong. Can you take a while again, dude?
I don't know. Maybe lost that negative sign.
That's it, standard form.
Yeah.
That's exactly what I did now that I'm looking at it.
Well, let's do something anyway. Here,
Sure.
let's do it. We'll do it anyway. But yeah, let's do this one or that one. But they're real similar in a way. But because what you need to do first, these are probably not separable. So you're doing the integrating factor method, and step 1 is
Standard form.
divide by this x. Put it in standard form by dividing by that x. You need this coefficient of 1 to start these problems. So, so now it looks like this. Everybody okay with that? Divide by x, get it into starting standard form for an integrating factor method. And then you find the integrating factor. The integrating factor is e to the integral of this coefficient, and this coefficient includes that sign. That's one warning I know students kind of can screw up there. That coefficient includes that negative sign. So this is not too difficult. This is e to the negative log x, I guess. But then I got to kill the e in the log. You have to kind of get this negative sign out of the way. So you have to employ that log rule that moves it up here. Then the e and the log cancel, and you have x to the negative 1. And that's the integrating factor. And you multiply through by it. Now, one of the things we were doing is after you multiply through by it, it's very automatic that the left-hand side turns into the derivative of the product of the integrating factor times y. That's after you multiply through by it, that's what the left-hand side is, so I write it as such. Don't forget you multiplied through by it, so your right-hand side has now been altered because you multiplied through by this, and your right-hand side is now just a sine x. So I sort of skipped a step there, but that's the step we keep skipping and we keep talking about what we skipped. So I sort of skipped that step, multiplying through and then rewriting the left-hand side. That's the 2 steps I did sort of in my head there, or whatever. Multiplied it through and rewrote the left-hand side. Cool, man, now you're almost home free. You take the integral of this side, you take the integral of this side. I'll just move over here. That would be x to the negative 1 times y when you integrate that other side. And then over here, you're just integrating a sine x. You know, and when I first looked at this problem, I thought I would be headed toward integration by parts, but the process has gotten rid of the integration by parts. I just have a nice integral of sine x here. I think that might be negative cosine x. Negative cosine x. So negative cosine x plus c. Now we're almost done. I want to solve for y. A lot of people might say divide by that, but because he's an x to the negative 1, I might want to say multiply by an x. Multiply by an x. That will get rid of that, and then if I'm multiplying by x, we're finished here. I'm multiplying by an x. When you multiply by an x, it's a variable, it's not a constant. It does not absorb into the c. You get this c times x. This is good. We're finished. We have a nice general solution. Yeah. So that was cool. Hey, any questions on that one? That was 9. He didn't really need my help. He figured it out himself. here was 10. Let's look at 10 while we're sitting here. It's real similar. Let's just try it. For 10, you divide by x. You divide by x. You divide by x to get yourself started. This is dy dx now. This is 2 over x times this y, and that's a 3 over x. And now I need to find the integrating factor. The integrating factor is e to the integral of that 2 over x. Well, what is that? That's e to the 2 log x, which is actually e to the log of x squared when you move the little 2 up. So then the e and the log cancel, so ultimately this is x squared. Your integrating factor is x squared. You multiply through by it. After you multiply through by it, the left-hand side becomes the derivative of the product of the integrating factor times y. The other side did get multiplied through by the x squared, and so it becomes a 3x. You guys okay? And then this turns out to be kind of an easy problem, I suppose. I'll just go right up above here. I'm going to integrate both sides now. The integral kills this derivative. I get x squared times y, and I integrate the other side. X squared divided by 2, right you guys? 3 halves x squared plus c. This is kind of nice. You divide by that x squared, and here's your answer. 3 halves, the number 3 halves, plus a c over x squared, I guess. That's kind of wild. Well, not that wild. That's that game. That's good. You know, the other thing we did yesterday was got toward the end of this section 2-3, there's a lot of little piecewise problems. And so we messed around with one of those. I did one out of the book. I think I did 38, but there's 37, 39, and 40 in the book. Sometimes I like to make up a little worse version of those, but it's good to do a piecewise problem. Yes, sir?
Just out of curiosity, are we allowed to skip the multiplying through step on the quiz test?
Well, right. So
Be careful.
yeah, be careful. But you know, and I'm grading steps, but your DE students, you have a certain amount of freedom. I mean, when you if you're smart enough to skip a step and not make a mistake, I'll try to. I mean, I know how to grade this stuff. I know how to read your work. The more steps you put in, the easier it is to read. I mean, you know, it's like skipping sentences. but I can, I can read your math. I've been practicing that for many years. So, but anyway, so I always advocate for clear communication between us. Yeah, that's what we're doing. We're communicating on paper to each other. We're communicating mathematics on paper to each other. And the clearer it is, the better it is. But if you're worried about skipping a step and he's going to take off a point because I skipped a step, I'm not really that kind of, no, I'm not really doing that. But showing your work, also helps. Listen, sometimes there's an integrity issue or a cheating issue. So, showing your work helps me that this didn't come from some mysterious folded piece of paper in my pocket, or this didn't come from some fancy calculator. I mean, anyway, showing your work helps verify that it came from your work, your head. So it's helpful to see as much as I can. So did I answer his question? I did a good job answering like a good lawyer would. I didn't. You're free to do kind of whatever you want, in a way. But again, we're communicating math to each other. It's kind of cool to pretend the reader. I mean, when you're doing math, pretend the reader doesn't know. Pretend the reader is not your genius professor. Pretend the reader is your kindergarten kid, and he needs to look at every step.
So we got to write out multiplication as 2 plus 2.
That's right. If he's a kindergartner, you're right. All right. Oh, don't go to an extreme. I didn't.
Piecewise.
Illustrate what 2 plus 2.
And bring my marbles.
You know, that's funny. But anyway, you know, 3 times 2. You know, what is 3 times 2? Well, it's 6. Yeah. But you're right. When you're talking to kids, I mean, and at some point you might forget this. You're an adult, you forgot that multiplication is addition. You know,
3 sets of 2.
It is 2 plus 2 plus 2. I mean, it is just fancy addition. It's a way of, and then if you, right. But then my kids were talking about, you know, what about the rules of positive and negative? So if you multiply 3 times negative 2, you guys know the rule. The rule is
Negative.
Positive times a negative is negative. But if you wanted to just try to explain that, why is that? Maybe you would say that what you're doing is you're adding 3 negative 2's. You know what I mean?
We're not going to do this on your on this quiz, I promise you that.
Anyway, it's fun and interesting to try to get to explain math at a real basic gut level sometimes. But that's it. Yeah. And then what if you're multiplying a negative 3 times a negative 2? I mean, we all know that's a positive 6, but if you try to explain that, holy shit. It's kind of... Maybe you factor this negative sign out and you think of it as this. With a negative sign in front of it. I don't know.
Teach a kindergartner factoring.
Anyway,
You
we're
have to teach them
off
about
track.
-1 coefficients.
I don't go off track too often. We won't. That's quick. What else? Any other good requests?
You were talking piecewise before we went into that.
Well, right.
What you're thinking about running more.
Right. I could grab one out of his foot. I could try to. Make up one. Yeah, I don't know. We could try this. Let's try this. So I'm in 2-3. Let's just try another one of these. Number 40, I guess, is a piecewise DE. It says it's 1 plus x squared, y prime, plus 2xy equals, and then what it equals on the other side is 2 pieces. The right-hand side is not just some function, but a piecewise function, and it is x and negative x. So it is an x when x is between 0 and 1, and then it's a negative x when x is greater than 1. So the right-hand side is a piecewise function. It's into 2 pieces. When we all right, just to get every little detail correct here. Actually, what it said in the problem is this is not equal to there, it's equal to there. The truth is, that hardly matters much to me, but just that's the way the problem was stated. But we worked on a problem like this yesterday. It's kind of tricky. What I would do is it's kind of one big DE, but when you get over to that right-hand side, you just sort of got 2 things to work with the whole time. But what's interesting is toward the end, when you finally get toward the end, when you integrate, you will have 2 sides over there, and you'll have a C1 and a C2. And then we got to deal with finding the C1 and the C2. So let's try this one. I think I'll try the integrating factor method. In order to do the integrating factor method, I do have a lot of writing here. I have to divide by this 1 plus x squared. So here I go. That's putting it into standard form. Dividing by this 1 plus x squared, and dividing by this 1 plus x squared. So I'm altering the look of this other side now. I'm dividing by 1 plus x squared. Okay, that's it. Again, I got these little notes off to the side here. Okay, now I need to find the integrating factor. I think I'll just work on that right here. That might take a little work because the integrating factor is e to the integral of this thing, 2x over 1 plus x squared. Well, maybe that's not that difficult, but it takes a little work. I got to do that integral, e to that integral. What would you do, guys, on that integral?
U substitute.
U equals the denominator. Du is the numerator. That's awesome. There is a little dx here. Okay, so du is the numerator, u is the denominator. This really just turned into a 1 over u here, didn't it? You with me on that? So it's a nice 1 over u, so it's the log of u. So it's actually e to the log of u. But now that e and the log can cancel, so it looks like this integrating factor is 1 plus x squared. That's the integrating factor. And now I'll multiply through by, this is what's so funny, that this problem was set up. You know, we're supposed to start in standard form, and then we go find the integrating factor, and then we multiply through by it. As soon as I multiply through by this, guess what I'm going to be? I'm going to be right back to where I started a few minutes ago. I mean, their starting form was actually 2 steps down the road. I didn't recognize it, but their starting form kind of was nice. But I went through the steps of dividing by this, finding the integrating factor. Here it is, and now when I multiply through by it, I'll be back to where I was a minute ago, won't I? Mm-hmm. I'll be exactly back to where I was a minute ago. So you multiply through by the integrating factor. You multiply through by the integrating factor. It puts you right back up above. That doesn't always happen, but on this problem, it puts me right back to that problem. And now, but then I recognize that the left-hand side is
Integrating factor.
the product of the derivative of the product of the integrating factor times y, right? And it equals that right-hand side, which is that right-hand side.
Bada bing.
Are you guys okay? Any questions?
Yes.
I found the integrating factor. I multiplied through by it. When I multiplied through by it, I realized it would look like that. But then what always happens is that left-hand side turns into, and it is, I can see it right now, I can see it, that left-hand side is the derivative of the product of the integrating factor times y.
So we could have jumped a step through just by looking at it if you knew better.
If I could see it then, and I could have maybe went with that, right? Right. Did you have it?
No,
All right.
I was gonna pray.
All right, good. Now you integrate both sides.
Praising that God.
Now you integrate both sides. And over there, I kind of got 2 little integrals to do. I'm working on this 2-piece. I got a damn right-hand side that has 2 pieces. Okay, this comes out to be 1 plus x squared times y, of course. And when I integrate the other side, I guess I get x squared over 2 plus a c, and I'm going to call that a c1 because when I integrate the other piece, I get a negative x squared over 2 plus a different c. It's technically a different c, a c2. You know, I forgot to write it down, but this problem did have an initial condition. Now that I'm 1 step away from the answer, there was an initial condition on this problem. It's bad of me to forget to write it down. I think it said y of 0 equals 0. So I'll get to that here in a minute because I'm almost finished. To finish this problem, you guys okay? I integrated both sides. To finish this problem, there's one more move. Well,
Get y by itself.
get y by itself. Y equals, I guess that's x squared over 2, and then I'm dividing by a 1 plus x squared. And then I have this c1, and I'm dividing by a 1 plus x squared. I guess this is a negative x squared, and this is a 2, and it's a 1 plus x squared. And I'm dividing this C2 by a 1 plus x squared. We're finished. We have this general piecewise solution. I mean, I keep saying we're finished, but there's a major work here at the end is to find C1 and find C2. Now let me just write these notes back in here. This top piece is valid for x's between 0 and less than 1. The bottom piece is valid when x is greater than or equal to 1.
So is it top solution only or top equation only?
Well, this is what we did. Here's the game. So I got to try to find C1 and C2. And usually what I think about that helps me find C1 and C2 is my initial conditions. But the initial condition is about when x equals 0. By the way, when x equals 0, y equals 0 is what it says. But really focus on the x equals 0. If x equals 0, that means your initial condition only applies to where x equals 0, which is this top piece. So your initial condition cannot apply to this bottom piece when x is greater than or 1. So that initial condition is not going to help you find C2. We need something else to help us find C2. But let's go ahead and use the initial condition to help me find C1. It does say when you plug in a 0 for x, you get a 0 for y. So across that top piece, I'm going to do that. I get a 0 for y if I plug in a 0 for x. If I plug in a 0 for x, I think I just got that. So what's C1? 0.
0.
Nil. C1 is 0. Cool. So now how do I find C2? I told you the initial condition helped me find C1, but now the initial condition doesn't apply down here because x is only greater than or equal to 1. I can't apply it when x is a 0. I need some other idea to get C2.
Limit as x approaches 1 from the left equals limit as x approaches 1 from the right.
Right. The other idea to help you find C2 was discussed yesterday, and what we said was we try to make this answer continuous. And what that means is we want this left-hand side to equal this right-hand side. When I call this the left-hand side, it's because it's less than 1, and this is the right-hand side because it's when it's more than 1. And I want them to equal each other at 1. That's called making it continuous. I want them to equal each other at 1. That means I'm trying to make it continuous. What it means is I'm taking the limit as x approaches 1 from the left of this function, and I'm setting it equal to the limit as x approaches 1 from the right of this function. I mean, that's technically what I'm doing. In order to find C2, I'm doing this, to find C2. What that boils down to is, and by the way, the 1 is here. This is the 1. This is why I chose 1. It's because of this. If this was a 2, I would do all this at 2. But I'm doing it at 1, and what am I doing? I'm doing this, okay? You don't have to really recall limits all that well. What you got to do is plug a 1 into here and set it equal to plugging a 1 into here. Right? That's what this is. So plugging a 1 into here would be 1 over
4.
Thank you, that's a 1 plus 1 is 2 times 2, that's a 4. Remember, C1 is 0, so this is totally gone because C1 is a 0. That's all just gone. So you're saying that's a 1 over 4, and I'm setting it equal to the right-hand side when x is a 1. The right-hand side when x is a 1 is negative 1 over 4 plus C2 over 2 when x is a 1. And I can find C2 with this concept. The initial condition helps you find C1. The concept of making it continuous is what helps you find C2 on these piecewise DEs. It's just a cool little thought at the end. This is not too bad. I'm going to add 1/4. When I add 1/4, I get 2/4, which is 1/2, equals C2 over 2. I'm going to multiply by 2, and guess what C2 is? A 1. So let's write our official answer. Our official answer is a piecewise answer, and it is now continuous. here's what it is. It's x squared over 2, parentheses 1 plus x squared. And this term that you thought you were adding is just a 0, so it's not there. It is that answer when x is between 0 and 1. And then it's this other answer here, negative x squared over 2, 1 plus x squared, plus this C2 over 1 plus x squared, which is a 1 over 1 plus x squared. And it's that answer when x is greater than or equal to 1. And we're finished. And we got a piecewise solution to this piecewise differential equation. And I like that. I mean, it's whatever. It's good stuff. One more thing. I'm not sure what these look like. I don't really want to go graph them. But between 0 and 1, it looks like something. And then to the right of 1, it looks like something else. But one thing I know for sure is it does, at 1, it does join up. We forced it to join up. We made it continuous. We made this continuous at the end. We found the C2 that made it match up and made it be continuous. So the final answer is a left and right hand piece, but they are continuous at 1. Cool. What else you want to practice? You want to, anything? Yeah.
When we go in the face
Yeah.
analysis,
Yeah.
if we're given a field and then given like a set of points, like a y of
Yeah.
1 equals something,
Yeah.
how exactly we're supposed to sketch that out?
Well, okay. So that's two different questions, but those, that's kind of, they're both kind of on today's quiz. So in 2.1, we learned about a slope field. And what I didn't do too many of these with you because I said you kind of look at them out of the book. So I'm going to grab one out of the book here. I'm looking at the book. I'm looking at this number 3. So at number 3 in the book, there's a slope field. Now look, I'm going to do my best to replicate this slope field. It kind of looks like it's a mess, but it looks like that, kind of. Now, this is the only question you're supposed to do. This is not supposed to be, this is a very easy question. Given an initial condition, like y of 0 equals 0, can you please sketch a possible curve that would go through that point? So that's the thing. When you read this initial condition, that's a point. So so you know it goes through here. And so that's kind of a starting point, maybe you could say. Now, can you follow these slopes and get a feel for what's going on? And I'm sorry, mine are kind of messy. It looks like to me, right here all along the x-axis, the slope is kind of up. So I think I'm going to head up. But now it looks like some of this is steering me back down, so I'm going to sort of head down and follow these slopes. If I head off to the left, it's really, you don't move to the left, but I'm trying to do these slopes sort of backwards and move to the left. I'm coming up with this. But it's just a drawing thing. It's trying to follow the slopes. And your slope field on your quiz will look better. It's more of a computer production out of the book. It wouldn't look like this one. I didn't draw a slope field by hand.
Which way you'd be going at each direction?
Well, you try to go both directions. Really, you kind of slopes kind of tell you as you move to the right, do you go up or do you go down? But I'm trying to, and I also try to draw the whole entire curve. So I do try to move to the left and right and draw a curve. Let me just try another one. Look, on this same slope field, can I do, here's another one. Y of -1 equals 0. Let's try that. So that's a different starting point. It's not that far over. It's right here. If I call this -1, I'll label. But if I started here, would I do something different? Maybe. You know, look at this. Again, if I start easing up to the right, this time, look, if I follow these slopes, maybe I head off here. See that? And if I go to the left, maybe it's still something like that. But depending on where you start, you follow the slope field, you might get a different looking shape. So that's one topic, slope fields. And it's, when you get your quiz, you'll get to practice it again. But yes.
Would you do a phase analysis one as well?
Sure. So then that's sort of a different question. Although, but there's sort of a connection to it, right? But sure. So a phase portrait analysis is sort of where 19 through 27. There's some more advanced discussions, 38, 39, 40. There's some interesting discussions. But did you have a particular request? I kind of interrupted you. Oh, 27. Yeah. Yeah, it's a weird looking one. Can I do a more normal one?
Yeah. I only asked that one because I had issues with it.
Yeah, I know. Yeah. But the one on the quiz and the one on the test will be, it won't look like that one.
My question is, when do you use the integrating factor theorem?
Well, that's a little off topic, but you don't mind, right?
I'll wait.
I mean, you're.
I just came up, popped up, man.
That popped out of your head, right?
You've just been doing it.
Well, I've been doing it today. I'm in section 2.3 when I do it, and I do it. The integrating, I only got two methods. I got the separation method in 2.2 and the integrating factor method in 2.3. Well, then I learned about Bernoulli up in 2.5 yesterday. But some things are not separable, so you can't separate and integrate. So then they got to be a first order linear DE, and they got to be in that certain form, and then I can do the integrating factor method.
First order linear DE.
Yep.
With the one y prime derivative.
Y prime and a y and then a function on the other side. I mean, they're kind of set up in this form.
Yeah.
Those separable ones can be kind of just a hodgepodge of stuff.
Separable ones, you're just trying to separate it into
y's and dy's
and dy dx on each side.
Right.
And if not separable, then use that theorem.
Right. Look at, so back to this phase portrait analysis, 26. Even though you asked about 27, let me just try this guy, 26. Here's this phase portrait analysis. It's really easy, actually. This is it, and here's the concept. The concept is a phase portrait analysis is, when does this equal 0? So you set this derivative equal to 0. And by the way, in all these problems, I didn't use this word yesterday, but in all these problems, they call these autonomous. And autonomous means there are no x's in this problem. There is only y's. And that's how all these kind of are. And anyway, so what we're doing is we're finding out when the slope is 0. We're finding when the derivative is 0. Back in Cal 1, we called those critical numbers. They were usually x values in Cal 1. Today, they're y values. When does this equal 0? When y equals 0, right, you guys? When y equals 2 and when y equals 4. These are called critical numbers. But, you know, to make a connection back to the slope field idea, here's what I just learned. When y equals 0, we have a slope, we have a slope of 0. So I can draw little slopes of 0 all along y equals 0. Also, at y equals 2, I have slopes of 0. So this is kind of like a little abridged version of my slope field. I've got slopes there, and slopes up here at 4. Up here at 4, I got slopes of 0. Now in between there, I might have slopes like this. Look at me. I don't know this. I don't know this. I don't really know this, but I might have those kind of slopes in between there. And then bam, boom, you have a slope field. So there is a connection between a phase portrait analysis and a slope field, but you don't really know this. You don't see all this, and you don't bother to go do it. What you do instead is just try to discover whether the function is increasing or decreasing in these intervals. So you pick a y value anywhere in any of these intervals. Let's start way up here. Above 4, can you pick a y value above 4? Let's pick 5. If I pick 5 and plug it into the derivative, is the derivative positive or negative? This is the derivative. If that's a 5, and that's negative, and that's negative, I think it came out positive. So it came out positive. That means when your derivative is positive, the function you're trying to draw is increasing. So the function is increasing. It's increasing. You can increase concave down, you can increase concave up, but there's only one that makes sense, because you have to leave this area here that has a slope of 0. So you have to leave a slope of 0 and somehow increase. So that's the damn picture, you guys. It is not this one. It is this style of increasing.
Makes sense.
It does make sense. It makes a lot. And so really, again, without doing a complete slope field, I kind of know that I got a slope field that's kind of doing that action right there. I mean, instead of doing the slope field, I decided that the derivative is positive for all these y values. If the derivative is positive for all these y values, the function is increasing from this slope of 0. It's got to have that look. Let's try something in between. Let's try a 3. So I'm plugging a 3 into this derivative. That's positive, that's negative, that's positive. When you multiply those three things, it's negative. If it's negative, it's decreasing. If you're decreasing from a slope of 0 to a slope of 0, this is your only hope. You look like that. And if we did a slope field for a bunch of points in between here, we'd see slopes that looked like that. We'd see slopes that guided us to that. But I'm not doing a slope field. I just found out I'm decreasing. I found these slopes of 0, and if I'm decreasing in between these slopes of 0, I gotta look like that. So this is cool stuff. Remember, this is 2.1, and it's before you're supposed to know how to solve DEs. So what we're learning is, shit, without even solving the DE, I'm getting a good looking picture of what the answer to the DE looks like, which I find pretty amazing. Without solving the DE, I know what the answer looks like. If it lives in this region or this region. See, again, the connection between the initial value is, if you had an initial value that said y of 1 equals 3, then where are you? Well, let's see. When x is 1, y is 3, you're right there. Now, would you know, again, you don't have a slope field here to guide you, but you have a phase portrait analysis to guide you. Would you know what to draw right there? I think I would draw something like this. Yes?
Yesterday, didn't you label them as stable?
Well, I wasn't really to that point yet, but yeah, hang on just a minute. Let's test this region. Plug in a 1. Plug in a 1. Positive, 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 it's positive. It's increasing. If you're increasing from a slope of 0 to a slope of 0, you gotta look like this. You got to. Let's try something down here, like a negative 1. That's negative, that's positive, that's negative. Ultimately, it's negative, it's decreasing. If you're decreasing from a slope of 0 to nothing, that's how you look. And then you're right. what we got here is critical numbers, and these critical numbers can be labeled or classified as repellers or attractors, and what's sort of synonymous with that is unstable or stable. So hang on, what about this guy, y equals 4? Y equals 4 was one of our critical numbers, and I look at this picture and I would call him a repeller, wouldn't you?
Will you only need one of those words? Or you can
Well, right. And yesterday I taught you that these words kind of go together. He's an unstable repeller.
That's at the critical number.
What we're doing is we're classifying the critical number as a repeller or attractor, stable or unstable. He's an unstable repeller. Why is he an unstable repeller? Because look, he's repelling. Nobody is being attracted to him. From the upper side, and from the lower side, nobody's being attracted to this critical number. He's a repeller. These words mean nothing to us except on today's quiz and on the test to Thursday you have to write down these words. Other than that, I don't have a lot to say about these words. I think they have some meaning if you study higher level differential equations and you run into this some of this phenomena again. Hey, what about this y equals 2? He was one of our critical numbers. I can now classify him after studying this phase portrait analysis. I can classify him as a stable attractor, right? A stable attractor, because those curves are being attracted from either side. Whether you have an initial condition here or an initial condition here, you get attracted toward this number. I mean, that's the way it works. No matter what your initial condition is, you get attracted toward this number. So this other initial critical number called y equals 0 can be classified as a repeller, unstable repeller. There's one situation that didn't show up here on this picture. We're finished with this problem, by the way. The other situation, though, is when you have one side comes toward it and the other side goes away from it, then you would call this guy semi-stable. He's kind of half stable. Do you agree? It's called semi-stable. Well, one side's getting attracted, one side's getting repelled. He's not a repeller, he's not an attractor, but he's half.
Mediocre.
He's semi-stable. Not a big deal. Very logical words, very common sense kind of use of those words. But that's good stuff from 2-1. That's on today's quiz and Thursday's test. You guys. So I went over all that to help you there. You know, his ultimate question he was asking me was about this 27. Let's take a quick look at this 27 he was asking me about. It's dy dx, and it equals y, and then it has the log of 2 plus y. Is that what it is? Y plus 2y, yeah. This is 27, and if I do a phase portrait analysis on this, I don't know. Let's think about it. All I do is set this equal to 0 and try to find places where my slope is 0. I mean, it's an easy start to this problem, and you can tell this one was all factored and very easy to set it equal to 0. Well, anyway, one of my answers is when this equals 0, y equals 0, so that's a critical number. And then the other thing is when does this equal 0? So when does a log equals 0? Well, kind of. I mean, well, no, that's not. Yeah, it does equal 0, maybe. Let's see. I guess I should do the steps to solve this. What would you do if you're doing some steps to solve this? You would e both sides. That would kill the log. You get 2 plus y equals 1. Subtract 2, and I just found another critical number, I guess. Y equals -1. That does make sense if I think of, I mean, I had a hard time thinking about it at first, but if I plug the -1 back in, 2 plus -1 is a 1. The natural log of 1 is 0. The natural log of 1 is 0. So cool. We found a couple critical numbers. We can play the same game at 0. There's a slope of 0. At -1, there's a slope of 0. And I can try to test in between. Now, what am I testing? I'm just looking at the sign of the derivative. I want to know if the derivative's positive or if the derivative's negative. It tells me about increasing or decreasing. I'll just try it real quick. If I try a 1, that's positive. I think that's positive. So it's positive. I mean, the log of a 3 is positive. It's positive, so it's positive. If it's positive, it's increasing. I know how to draw an increasing thing. What about in between here? I need to try like a -1/2. That's negative. That's -1/2 plus 2. That's 1.5. The log, that's positive, I think. So I get a positive. It's the log of that. And I think it's positive, but that's negative, so it's negative. If it's negative, it's decreasing.
Well, natural log was 0.5. Oh, wait, negative 0.5.
And wait a minute. It was negative 0.5 added to 2. See that? So added to 2, it was a 1.5.
Gotcha.
Yeah, and the natural log, I mean, you can pick up a calculator, but yeah, I think it's positive. But you're right, you kind of need to know that. And what if I try -2, that's bad. That's, I can't go below. Actually, I can't have a -2 because I can't have the log of 0. So -2 is kind of like nothing exists down here. Huh. That's a no man's land.
DNE.
Well, I could try -3/2. That would be negative. That might come out negative, which would be positive, which would give me this look, I think. I just tried -3/2. I couldn't really try -2 or below. That's kind of like a black area.
Yeah, it would be
So anyway, that was cool. But it was a little different. All right. Well, we've sort of killed an hour. What else you guys want to do? You want to do anything else? You want to take a break and take a quiz?
I had one quick question.
Sure.
Is there anything important you think we should know in 1.2 quiz?
Oh, I don't know.
And it came on DNE.
I mean, there were some good questions in 1.1 and 1.2. We were verifying DEs. We were finding some Cs. There was some other interesting stuff toward the end.
And then plug that into it.
What did you just do with that Y over there?
Okay.
I don't know. What do you mean?
Well, I know you took put E to the L and to get 2 plus Y is equals either 0. What would you do with the Y in front?
This Y?
The other Y.
Out front.
Yeah.
Right. So so I'm asking, when does this slope equal 0? So I set this equal to 0, and then these are multiplied together. So I set each factor equal to 0. So I set this guy equal to 0, and that produced
0.
that answer. And so that's one of the critical numbers. Is Y equals 0. That was this guy, and I was testing, and that has a slope of 0, and I was testing around that. The other critical number came from setting this equal to 0, e'ing both sides, and we got this other critical number, right?
Okay. You set both sides equal to 0.
So those are my critical numbers, and then I was testing between them. Yeah. 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 So.
Aren't they also critical numbers if they're undefined?
Yeah, that's true. I mean, so back in Cal 1, the theme was, if you're looking for critical numbers, you take a derivative and you ask yourself 2 questions. When is the derivative 0? And when is the derivative undefined? Because those both could possibly lead to critical numbers. You're right. In these particular problems, asking when these are undefined, it turns out to be usually never. So it's mostly about when does it equal 0. Yes?
But wouldn't that definition make, the one about undefined, wouldn't that make this have an infinite many critical numbers?
Well, the other little part of the definition of critical numbers is they had to be defined in the original function. So we don't know about the original function. Your point is, I should look for places where this is undefined.
No, I'm just wondering.
You're wondering. Well, but anyway, no, they're not gonna be good places. But if I did pursue that thought, when is this undefined? And I sort of discovered it as I kept talking here. It's undefined when y is less than or equal to -2. So all those y values, you're right, there's thousands of them. -2.1, -2.111, -2.2. Anyway, everything less, there's thousands of places where it's undefined. Everything less than -2 is undefined. They're not places with slopes of 0 though, so I don't draw them with slopes of 0 like a phase portrait analysis. It's just I can't have these y values, so I was describing it as this big dark zone of illegal y values. So not critical numbers. I wouldn't list these as all a bunch of critical numbers. What else? Well, let's do what I said. What did I say? I said take a quick break and come back and take a quiz. So about a little 7-minute break, and then we'll come back and try a quiz. It'll be about a 40, 50-minute quiz. That's all you need, I think. So a quick break. Come back and do a quiz. I'll hit pause and off on this thing.